Top-down atmospheric inversions are the primary tool we use to track global methane. By observing the concentration of gas actually present in the atmosphere, these computational frameworks work backward to infer where that methane came from, mapping surface emissions across the globe. This accounting relies on a simplified equation: atmospheric methane change equals total emissions minus chemical loss. Expanding that loss term reveals one crucial variable: the hydroxyl radical, OH. It is the primary chemical sink that clears methane from the sky. Because inversions measure total methane burden directly from atmospheric data, they have to deduce the emissions. They do this algebraically, subtracting the modeled chemical destruction from the observed methane concentration. Whatever is left over is recorded as the surface emission. But you can only solve that equation if you know exactly how much hydroxyl radical is present. To make the math work, many inversions prescribe their OH fields using static climatology or externally specified uncoupled trends. This architectural choice is computationally efficient. Running fully interactive, real-time chemistry for every air parcel on Earth requires massive processing power, so fixing the OH baseline keeps global models agile. That efficiency creates a structural vulnerability. When intense climate-driven variability alters the oxidant levels over the ocean, the fixed OH baseline in the model fails to capture the true chemistry happening in the air. Recent kinetic modeling isolates a specific pathway that triggers this failure. It is called the marine radical pump. Driven by extreme temperature and wind, it forces a massive reorganization of atmospheric chemistry that distorts OH baselines. Relying on static chemical assumptions during these active marine anomalies creates a systemic attribution error. The inversion model misinterprets chemical changes in the sky as physical changes on the ground. To see exactly how missing data breaks the framework, we have to look at the mathematical logic governing the grid. The system remains accurate only when assumed chemical loss perfectly matches true chemical loss. When true chemical loss rapidly outpaces the prescribed model, the scale tips. To reconcile the unexpectedly low methane concentrations with the weak assumed chemical sink, the model artificially drops inferred surface emissions. The physical requirement to trigger this exact error is a sudden unmodeled local spike in OH. Any localized surge in hydroxyl radicals scrubs the surrounding air of methane. To a rigid model, that missing gas registers as a fictitious drop in emissions from the land below. That local surge originates at the surface of the ocean. The marine boundary layer contains a massive reservoir of biologically produced halocarbons, most notably bromoform. This equation defines the atmospheric source rate of bromoform outgassing. The rate depends entirely on the sea-to-air flux pushing the gas upward and the effective mixing height trapping it. This upward flux is controlled by temperature-dependent solubility and wind-driven gas transfer. We can model the exact thermodynamic forcing of a marine heat wave by applying a positive 3 degrees Celsius perturbation to the sea surface temperature. Following the Van Hoff equation, that specific thermal shift decreases the solubility coefficient of the water by 15.9%. The warmer ocean physically loses its capacity to hold dissolved bromoform, forcing the gas toward the surface. We couple that heat wave with the kinematic forcing of a storm, increasing the surface wind speed from 5.0 to 12.0 meters per second. The model diagnoses the result of this combined forcing. The ocean-to-atmosphere source rate amplifies by 583.8%. This is a coupled thermodynamic and kinematic event. It is the raw velocity of the storm violently stripping gas from a thermally saturated ocean. Extreme weather anomalies forcibly ventilate the oceanic halogen reservoir, injecting massive concentrations of bromoform into the lower atmosphere. Once airborne, bromoform activates a 6-species chemical network. Atmospheric degradation breaks the bromoform down, releasing active bromine. This bromine immediately reacts with ozone to form bromine monoxide. The bromine monoxide then draws down the existing HO2 pool to synthesize hypobromous acid, or HOBr. Sunlight strikes the newly formed HOBr, splitting the molecule. This regenerates active bromine and injects newly formed OH directly into the atmosphere. The pump does not rely on an external source of oxidants. It actively scavenges hydroperoxyl and converts it directly into hydroxyl, reorganizing the local chemical partitioning. The cycle runs continuously until closed by a terminal physical loss. Sea spray scrubbing captures the HOBR, pulling it back into the water. This chart tracks system equilibration. The cold marine baseline takes nearly 35 days to reach steady state. The storm anomaly takes less than 13. The cold water retains high dissolved reservoir capacity, creating chemical inertia and a slow overshoot. The storm anomaly is entirely source-dominated, slamming the atmospheric radical pool into a rapid, elevated plateau. At that rapid equilibrium, the warm, wind-enhanced anomaly state increases the local steady-state OH concentration by 25.67. When that hyperoxidative air mass moves off the ocean and sweeps over land, the theoretical chemistry collides with real-world meteorology. Because methane lifetime is inversely proportional to OH concentration, a local 25.67% enhancement in hydroxyl yields a 20.43% reduction in the chemical lifetime of methane. As the storm system rolls over coastal infrastructure, agriculture, and fossil fuel production zones, it encounters dense terrestrial methane sources. The spiked OH baseline immediately begins scrubbing the methane out of the sky at a velocity far exceeding standard climatological predictions. A top-down inversion, assimilating satellite and ground data, registers this exact event. It observes an unexpected drop in local atmospheric methane over the region. But if the inversion uses prescribed OH fields, it is completely blind to the marine radical pump. It processes the methane reduction against a static baseline that assumes the chemical sink has not changed. To balance the equation, the model relies on the only remaining variable. It concludes that local farms, landfills, and oil and gas facilities must have simultaneously reduced their output. This misattribution compromises emissions inventories. When policy decisions are built on models that alias sink variability into source variability, recorded reductions in industrial emissions are nothing more than computational artifacts. To correct this, inversions must adopt dynamically updated OH fields, explicit marine halocarbon precursors, and wind-dependent gas transfer algorithms. Methane accountability requires precision. Until inversion architectures integrate the atmosphere's dynamically changing capacity to clean itself, extreme weather will continue to distort our understanding of global emissions.